Forging is like shaping dough with your hands. The metal is pressed or hammered until it takes the desired form. The industry sorts forging methods into families based on how the material is confined while it deforms. Open die free forge. The workpiece is squeezed between two flat or slightly curved anvils with no side walls, similar to flattening a piece of clay on a board. The shape is limited to simple bars, rings, or discs, and material flows outward in all directions. Closed die impression die, also called drop forging, two matching die halves enclose the workpiece completely, like a cookie cutter. When the hammer drops, the metal fills the cavity and takes a complex shape in a single stroke. Subcategories. Impression dies have a defined cavity, the metal is forced to fill it. Full close, both halves close completely, leaving very little flash. Partial close, only a part of the cavity is closed, the rest is filled later. Roll forming, also called roll forging, a series of rollers progressively bend and stretch the metal, much like rolling a piece of paper through a press to create a long, thin shape. It is ideal for long, slender products such as ribs, beams, or automotive rails. Other special names include cross-ram forging, two hammers strike opposite sides, and preshot, preheating and initial shaping before final die work. Understanding the nomenclature helps the engineer pick the right process for cost, material flow, and part geometry. Open die simple low-cost tooling, high material waste, good for large parts. Closed die high precision, low scrap, higher tooling cost. Roll forming continuous production, excellent for long parts. These categories act like the family tree of forging, guiding designers toward the most efficient route. A forging die is the mold that gives the metal its final shape, and its design follows a few easy-to-remember rules. Think of it like carving a wooden block. Draft angle, just as a wooden sculpture needs a slight taper so it can be pulled out of the carving block, a die cavity must have a small taper, usually 1 to 3 degrees on the walls. This prevents the part from sticking and reduces the force needed to open the die. Fillet radius, sharp corners are stress razors, much like the corner of a broken glass. Adding a generous fillet approximately half to 1 times the metal thickness smooths the flow of material, avoids cracking, and reduces wear on the die surface. Parting line, this is the line where the two die halves meet, similar to the seam on a two-piece pizza pan. Placing the parting line on a plane of symmetry or on a low-stress region makes the part easier to eject and reduces the chance of a flash excess metal. Die material selection, the die must survive repeated impacts at high temperature. Common choices. H13 tool steel, excellent toughness and heat resistance, used for hot forging. W2 tungsten carbide, very hard, low wear, for cold forging high volume parts. Maraging steel, high strength, used for aerospace components requiring very tight tolerances. Cooling heating passages, imagine blowing air through a straw to cool a hot drink. Internal channels in the die circulate oil or water, controlling die temperature so the metal flow stays predictable and tool life is extended. Surface finish, a mirror smooth finish raw less than or equal to 0.2 micrometers produces a smoother forged surface, reducing post-process machining. The design is a balance. Too much draft makes the part oversized, too little fillet can cause cracks, wrong material leads to premature die failure. By visualizing the die as a reusable kitchen mold, the engineer can keep these rules in mind while drawing the CAD model. The forging load is the force the press must supply to push the metal through the die. It can be estimated with a simple flow stress model. Sigma equals K sigma Y, where sigma equals true flow stress at the forging temperature. Sigma Y equals yield strength of the material at that temperature. K equals strain hardening coefficient, often 1.2 to 1.5 for hot forging because the material softens as it deforms. Step-by-step example, hot forging of a steel bar. Material data AISI 1045, 1150 degrees Celsius. Sigma Y equals 120 megapascals. For hot forging, take K equals 1.3. Sigma equals 1.3 times 120 equals 156 megapascals. Determine the projected area of the deformation zone, A, for a simple upset of a 50 mm diameter billet to a 60 mm length. The projected area is the cross-section area. A equals pi d squared over 4 equals pi times 0.05. squared over 4 equals 1.96 times 10 to the minus 3 meters squared. Compute the required load Fs. F equals sigma times A equals 156 times 10 to the 6 pascals times 1.96 times 10 to the minus 3 meters squared equals 3.06 times 10 to the 5 newtons. Approximately 306 kilonewtons. Add a safety factor SF of 1.2 for friction and dynamic effects. F design equals SF times F equals 1.2 times 306 equals 367 kilonewtons. Choose a press with at least this capacity. A 400 kilonewton hydraulic press would be suitable. Key points. The flow stress can also be expressed with a Halaman equation where epsilon is true strain and n is the strain hardening exponent, approximately 0.15 to 0.3 for hot steel. For a more accurate load, integrate sigma over the deformation path. Sigma equals K epsilon to the n. Friction factor M, 0.05 to 0.15, is multiplied by sigma and the contact area to add to the load. For closed die forging, the load may be 2 to 3 times the open die value because the metal is confined. Material choice is the backbone of any forging operation. The rule of thumb is hot forge when the metal is above its recrystallization temperature approximately 0.6 to 0.8 times the melting point, where Tm is the melting point in Kelvin, and cold forge when it is below that range. Temperature reduces yield strength dramatically. For example, AISI 4140, 1200 degrees Celsius to sigma, Y approximately 150 megapascals versus 850 megapascals at room temperature. Allows large deformations in a single step because the material continuously recrystallizes, eliminating work hardening. Typical temperature window, 0.7 T sub M plus minus 30 degrees Celsius. Materials commonly hot forged are carbon steels, alloy steels, stainless steels, aluminum, titanium, and copper alloys. Cold forging is done at or near room temperature. The material retains high strength, leading to higher part strength and better surface finish. It requires higher loads, often 2 to 3 times hot forging loads, and may need multiple stages. Suitable for high-strength steels, for example spring steel, and aluminum alloys where dimensional accuracy is critical. Material charts. AISI 10045 carbon steel, melting point 1530 degrees Celsius. Recommended hot forge temperature 1150 to 1250 degrees Celsius. Typical yield strength cold 550 megapascals. 7075 aluminum, aluminum zinc magnesium copper alloy, melting point 477 degrees Celsius. Recommended hot forge temperature 350 to 400 degrees Celsius warm. Typical yield strength cold 480 megapascals. Titanium 6 aluminum 4 vanadium, melting point 1660 degrees Celsius. Recommended hot forge temperature 1000 to 1200 degrees Celsius. Typical yield strength cold 880 megapascals. Temperature strain stress relationship. Sigma equals a times exponential of negative b times t times epsilon to the n. Where a, b, n are material constants, T is absolute temperature in Kelvin and epsilon is true strain. As T increases, the exponential term drops, lowering sigma. Practical tip: use a critical forging temperature chart. For example, for low carbon steels, the critical temperature is about 950 degrees Celsius. Forging below this leads to excessive strain hardening and risk of cracking. Choosing the right material temperature pair ensures the metal flows smoothly. The required press capacity is realistic, and the final part obtains the intended mechanical properties. Explanation: forged parts can hide a variety of defects, each with a distinct look-feel. Here is a quick checklist using everyday analogies. 1 lapse or lapses: imagine 2 layers of pastry dough that have slipped over each other and are not fully pressed together. In forging, a lap occurs when a surface folds onto itself, leaving a thin, unmelted pocket. Diagnostic surface inspection shows a shallow trough cross-section reveals a double layer with a clear interface. 2 cracks like a dried bread crust breaking when you pull it. Cracks arise from excessive tensile strain, low temperature, or high strain rate. Diagnostic visible line on the part, often perpendicular to the flow direction X-ray or ultrasonic testing, shows a discontinuity. 3 folds similar to a folded napkin left in a sandwich. Excess metal folds back on itself, creating a step or ridge. Diagnostic local thickness, increase visible ridge after polishing metallography, shows a reversed flow line. 4 cold shuts, think of spreading frosting too quickly on a cold cake. The 2 flows meet before fully fusing, leaving a weak line. Diagnostic thin line on the surface, often on the outer radius of a forged ring microscopy, shows a lack of grain bonding. 5 flow lines or shear bands comparable to the layered pattern you see in laminated dough. These are zones of intense shear where the grain is highly elongated. Diagnostic visible striations on the surface EB-SD maps show high misorientation. Temperature too low cracks, lapse, cold shuts. Excessive die clearance folds, lapse. High friction surface cracks, uneven flow. Improper die design, draft angle, fillet radius, concentration of strain, leading to folds and cracks. Visual inspection, die penetrant testing, ultrasonic echo radiography, and metallographic cross-sections. Early detection prevents costly rework and guarantees component reliability. After forging, heat treatment tailors the microstructure to achieve the desired strength, toughness, and dimensional stability. The 4 most common cycles are: normalizing, heat the part to austenitizing temperature, approximately 0.8 times T sub M, hold for a few minutes, then air cool. It produces a uniform, fine-grained ferrite perlite structure, reducing residual stresses. Analogy, like baking a loaf of bread and then letting it cool on a rack. The cool down is uncontrolled, giving a consistent crumb. Quenching, heat to the austenitizing range, then rapidly cool in oil, water, or polymer. This traps carbon in solution, forming hard martensite. Analogy, dropping a hot metal spoon into cold water, it solidifies instantly. Tempering, reheat the quenched part to a lower temperature, 150 degrees Celsius to 650 degrees Celsius, and hold, then cool. Tempering reduces brittleness by allowing some carbide precipitation, improving toughness. Analogy, softening hardened chocolate by gently warming it. Annealing, heat to a high temperature, hold long enough for recrystallization, then slow cool, furnace cool. This yields a coarse, soft microstructure ideal for subsequent machining. Analogy, letting a hot glass melt slowly so it becomes uniform and stress-free. Effect on mechanical properties, example for 4340 steel. Normalized, hardness 250 HB, tensile strength 950 megapascal, toughness 35 joules. Quenched and tempered 200 degrees Celsius, hardness 380 HB, tensile strength 1550 megapascal, toughness 12 joules. Annealed, hardness 150 HB, tensile strength 700 megapascal, toughness 45 joules. Practical tip: the forged shape often dictates the cooling method. Thick sections need oil or polymer quenching to avoid cracking, while thin sections may be water quenched for faster cycles. Choosing the right cycle ensures the part meets its design specification without unnecessary distortion. Forging dies are exposed to high impact, temperature, and abrasive metal flow. They wear down like a runner's shoes on a marathon track. The main wear mechanisms are: Number 1, abrasive wear. Hard particles, for example oxides and carbides, scrape the die surface, similar to sandpaper rubbing wood. Described by Archard's law. V equals K times W times L divided by H. V equals wear volume in cubic millimeters. K equals dimensionless wear coefficient, approximately 10 to the minus 4 to 10 to the minus 6 for steel on steel. W equals normal load in newtons. L equals sliding distance in millimeters. H equals hardness of the softer material in megapascals. Number 2, adhesive wear. Material sticks to the die and pulls away, like chewing gum adhering to a shoe sole. It is aggravated by high temperature and insufficient lubrication. Number 3, thermal fatigue. A repeated heating and cooling causes micro cracks, akin to a metal bridge expanding and contracting daily. Number 4, oxidation wear. At forging temperatures greater than or equal to 900 degrees Celsius, oxide layers form and spall off, taking die material with them. Life prediction model. Engineers often use a hardness temperature time index. HTT equals H times E to the minus Q over RT times T. where H is die hardness, Q is activation energy for oxidation, R is the gas constant, T is absolute temperature, and T is cumulative exposure time. A higher HTT indicates longer die life. Practical example: die hardness equals 55 HRC, approximately 1,800 megapascals. Forging temperature equals 1,150 degrees Celsius, which corresponds to T equals 1,423 Kelvin. Assuming Q equals 300 kilojoules per mole, T equals 5,000 seconds. Plugging values gives an HTT value that can be compared against a chart derived from test data to estimate the number of forgings before a regrind is needed. Mitigation strategies: use coatings, titanium nitride or chromium carbides to raise surface hardness. Optimize die cooling to keep temperature below critical oxidation thresholds. Apply lubricants such as graphite or molybdenum disulfide to reduce adhesive and abrasive wear. Understanding these mechanisms lets a shop plan die maintenance, schedule regrinds, and control production costs. Below are 5 typical exam-type questions with concise model answers. They cover theory, calculations, and defect analysis, the exact style you might see in a B.Tech or MBA in manufacturing exam. Question 1. List and briefly describe 3 major categories of forging processes. Give 1 example application for each. Open die free forge. Metal is deformed between 2 flat or simple-shaped anvils, no side confinement. Example: upsetting billets for crankshafts. Closed die impression die. 2 matching dies enclose the workpiece. Material flows into a cavity. Example: automotive connecting rod. Roll forming, roll forging. Consecutive rollers progressively shape a long workpiece. Example: production of railway rails. Question 2. A 60mm diameter steel bar AISI 1045 is hot forged at 1,150 degrees Celsius. Its yield strength at this temperature is 120 megapascal and K equals 1.3. Calculate the minimum press capacity required for a single stage upset, assuming a safety factor of 1.2 and friction factor of 0.1. Step 1. Flow stress sigma equals K times sigma sub Y equals 1.3 times 120 equals 156 megapascal. Step 2. Projected area A equals pi d squared over 4 equals pi times 0.06 squared over 4 equals 2.83 times 10 to the minus 3 square meters. Step 3. Basic load F equals sigma times A equals 156 times 10 to the 6 multiplied by 2.83 times 10 to the minus 3 equals 441 kilonewtons. Step 4. Friction load F sub F equals m sigma. A equals 0.1 times 156 times 10 to the 6 multiplied by 2.83 times 10 to the minus 3 equals 44.1 kilonewtons. Step 5. Total load F total equals F plus F sub F equals 485 kilonewtons. Step 6. Apply safety factor. Design load F design equals 1.2 times 485 approximates 582 kilonewtons. Required press capacity approximately 600 kilonewtons. Question 3. Explain why a lap defect is more likely to occur in a hot forged component than in a cold forged one. Answer 3. In hot forging, the metal is softer and flows quickly. If die clearance is too large, the surface can fold over itself before full die contact, creating a lap. In cold forging, the higher strength restricts excessive flow, and the material tends to shear rather than fold, making laps less common. Question 4. Sketch a normalizing heat treatment cycle for a forged 4140 steel bar. State the purpose of each stage. Step 1. Heating to 845 degrees Celsius, approximately 0.85 times the melting temperature, transforms microstructure to austenite. Step 2. Holding 10 to 15 minutes, ensures uniform temperature throughout the section. Step 3. Air cooling to room temperature, produces a fine-grained ferrite pearlite structure, relieving residual stresses and improving toughness. Purpose: refine grain, homogenize composition, improve mechanical properties. Question 5. Using Archard's wear law, estimate the wear volume after 2,000 seconds of forging if the normal load is 400 kilonewtons. Sliding distance per stroke is 25 millimeters. Number of strokes equals 500. Die hardness is 1,800 megapascal, and K equals 2 times 10 to the minus 5. Total sliding distance, L, equals 25 millimeters times 500 equals 12,500 millimeters, equals 12.5 meters. Load W equals 400 kilonewtons, equals 4 times 10 to the 5 newtons. Where volume V equals K times W times L divided by H equals 2 times 10 to the minus 5 times 4 times 10 to the 5 times 12,500, divided by 1.8 times 10 to the 9, approximates 5.6 times 10 to the minus 4 cubic millimeters. Result: negligible wear, indicating the die material and coating are adequate for the given production run.